Hey, Kelly. See, I saw you post your lecture too. So that's good. And she went over dehydration of alcohol and E2 reaction, which we went over last night. So that's pretty good. Did she go over that in today in like class? Let's see. Hey, Elysia. Oh, Elysia, not Elysia.
Yeah, you got it. Hi.
Mm-hmm. I finally know how to pronounce your name. Elysia, not Elysia, right?
Yeah, that's cool.
Yeah, that's good. That's good. How have you been?
I've been pretty like I give myself a lighter load this quarter for sure.
Oh,
Not
like
doing
lighter quarter this quarter, like less classes, less units,
less stems.
less
Oh
stems. That's good.
yeah, I'm doing like one GE. It's like linguistics or something.
Oh, linguistics. Yes, yes.
Yeah,
See, that's
yeah, and
good.
then not too bad.
Uh-huh. Oh, like is that like LIN 001?
Yeah, like
Oh my
0, 0.
gosh. Yeah, I took that class too.
Did you? How was
Yes.
it?
It was kind of funny because like I did not pay attention at all in that class, so you can have a pretty chill time.
Well,
Um, yeah.
ours is recorded. We don't have an in person.
Oh, yours is recorded. That's pretty good. So yeah. Who's your professor or instructor?
I just know it's a lady,
Oh, it's
but
lady.
yeah.
Yeah, I see. I had a guy instructor. The hardest part about the class was the group project at the end of the quarter. We had to present um
What?
things. Yeah, and we
Ooh,
had no idea because like none of us paid attention, or like most of us didn't pay attention. But luckily, I had a group mate who did pay attention in class. 'Cause they asked questions about the project, and then like we had no idea how to answer it.
ooh, that's not good.
I know.
This was in person that you did it, or what?
Yeah, it was an in-person group presentation. Like we had to meet somewhere like on campus, like in the field, like in the grass, and then present our poster. It was
Okay.
not fun.
Not fun?
Yeah, it was not fun because like I didn't pay attention. I should have, but I didn't, and then I didn't know what was going on.
That's wild.
Yeah.
At least I know that it's like pretty easy to pass then if
It is, yeah. Right.
how about
Mhm.
you? What did you do this spring break or so far?
Yeah, in spring break, like last week, I slept a lot because, like especially after the last quarter's finals, like doing the review sessions, the final private sessions, studying for my own finals, lecture finals, lab finals. So like I caught up on a lot of sleep for sure. Walked my dog a lot more. Caught up with friends. Uh, I went to my chiropractic friend's house so to practice like adjusting skills, just so that we don't get rusty when we get back.
Mhm.
Yeah, and that's pretty good because I always have something in my lower left neck area, and my friends always like adjust me in that area, so it always feels nice after. It's like a reset.
Oh, that's nice.
Yeah.
That's good you're taking your dog out for more walks.
Yes, like at least two times. I want ideally three, but at least two, like one in the morning, one in the evening.
Yeah, that's
Yeah.
going out on their walks is how they socialize with other dogs without our
Yes.
them.
Mm-hmm. Right. See. Do you have a pet? Oh yeah, you do have a dog, right? Like
Yeah,
from the
you remember
forest
his
app.
name? I
His
told you his
name?
name before.
You told me his name before?
Yes.
Oh my God. You did not tell me his name before.
Yes, I did.
When did
I,
you tell me?
okay, well, I told you he's a Chihuahua, so that should
Yes.
give it away. His name. It's
Chihuahua.
not. It's not like a common name. It's kind of like a. I don't know. It's kind of funny.
Uh, Boxer. No,
No,
I don't know. I don't know. That's like a bulldog name.
it's the opposite of little bit.
Little bit. A lot.
Well, Biggie.
Biggie. You did not tell me this. I did not remember you telling me
Small.
this,
Yeah.
Alicia.
No, I did tell you though.
On Discord or on Zoom? Oh my gosh. You
Oh,
did
I
not
showed
tell
you the
me.
dog and you asked me what's his name.
Oh my gosh. Oh my gosh.
It's fine.
Uh,
You'll remember his name next time I ask you.
yes, Biggie.
Yep. But I'll be back. I'm gonna go switch on my lunch.
Okay. Yeah. So Kelly, we're gonna do 118B reactions. We'll review how to make alkenes, E2, and dehydration of alcohols, and after that, we'll start with the electrophilic addition reactions. Yeah. 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 What is your naming question? You could send it to me through text, and then I could pull it up here. How was your car? Like how long did you like stay at the Arc until it was fully charged and you drove back? Like at midnight or something last night? The substituents portion thingy in her slides, I stated because they closed, but it wasn't fully charged. Oh, I see. But you were able to drive back home though. That's good. So let me check her lecture slides. Substituent portion of her lecture slides. What slide is that? Slide. Let's see. Slide. Is it the EZ system? Last bit of the part labeled lecture 1. Okay, last part of lecture 1. Substituents containing a double bond are named alkenyl. For example, ethenyl, common name vinyl, 2 propenyl, allele, and cis 1 propenyl. Ethenyl, 2 propenyl, cis 1 propenyl. Practice. Trans 3, 2, 3, 1, 2, 3, 4, 4 pentenyl, cyclooctanol. Okay. So if the alkene is not the priority in nomenclature, right? Meaning that the alcohol takes priority over alkene. So if there's an alcohol present in the molecule, the alcohol takes priority. So that means the base of the nomenclature is going to be OL, ol. The alkene becomes a substituent. Right? Meaning that if alkene is not the main chain, the base name would not be ene. The alkene would be a substituent, which means that it would be enol. Right? It would become an alkenol. Right? And depending on how long the substituent is, if it's like 5 long, like 1, 2, 3, 4, 5, as a substituent, then that's pentenol, and it is coming off of carbon 3. So this is going to be 3 pentenol, right? And we're going to look at the example that she gave as practice. Is that the thing under alcohol supposed to be OH? No, this is ol, OL, meaning that the base of the nomenclature ends in OL, ol. Right? That's if you have an alcohol present in your functional group. So let me show you the example as she gave in the lecture slides, which is this right here. We have two functional groups here in this molecule. We have an alkene and we have an alcohol. We also have a big ring here, and this big ring is 1, 2, 3, 4, 5, 6, 7, 8 carbons long, which is bigger than this 1, 2, 3, 4 chain right here, right? And we also see that the alcohol would have higher priority than the alkene in nomenclature, meaning that when we number our structure, it's going to start here. Our carbon 1 is right there, right? And we want to number it in a way where the next substituent is the lowest number possible. So in this way, we're going to rotate this direction, which is, I always get this messed up. This is counterclockwise. Yes, counterclockwise. Right. So we see at carbon 3, this whole molecule here, that whole alkene part right there is the substituent. This is not part of the main chain. The main chain is this 1, 2, 3, 4, 5, 6, 7, 8 part right there. So I could highlight the main chain in yellow like this, which is this 1, 2, 3, 4, 5, 6, 7, 8 main chain right there. This part of the molecule is a substituent. It's not part of the main chain. Numbering the substituent off of the main chain, we have 1, 2, 3, 4, 5 carbons coming off of the main chain, right? And we see that it is alkene, where the alkene starts at carbon 4. So this substituent is 4, because this whole substituent here is 5 carbons long, is 4 pentenyl, right? This 4 here represents where the alkene starts at. If it was 3, then our molecule would look like this, where this would be a single bond, this would be a double bond, right? So we could say that our main chain is cyclooctanol because it's a 8-membered ring, and the ring is the cyclo part. Cyclo, and if it's 8 oct, and it's not ane, it's not cyclooctane, right? Because we have an alcohol. So we're gonna omit the E and add the OL because we don't want to have two vowels next to each other. We don't want to have like this. Right, we're gonna drop the E and have O right there to represent this alcohol. And then we're gonna plug in the substituent for pentenyl right here. And we're gonna include stereochemistry now, where we see that the alcohol is a dash going away from you, and this whole substituent here is a wedge going toward you. So they are trans to each other. So we could put trans in front of the name to include stereochemistry in its nomenclature. Any questions on that, Kylie? On that nomenclature? So the big important thing here is that this alkene is no longer the priority, right? It's a substituent. The priority is this yellow highlighted part of the molecule, the 1, 2, 3, 4, 5, 6, 7, 8. The alkene is now a substituent, which becomes an enol, alkenol. The trans is for the alkene portion? No, the trans is for the stereochemical relationship between the alcohol and this whole group right there. This alcohol is a dash. This whole group right here is a wedge. They're opposite from each other, making it trans. We cannot assign cis or trans for this alkene because this carbon here of the alkene has 2 hydrogens. Both of these groups here have the same priority. So that we cannot assign cis or trans or E or Z for this alkene. The trans here is talking about this whole group right here that I boxed out, and this alcohol right here, right? This alcohol is dash, this whole group is a wedge. Let me give you an example problem where the alkene is the substituent. Okay, try this one out, and I'll check your work after. I'll give you a hint. There's two stereochemistry things you have to worry about here. One is going to be R or S. The other one is going to be E or Z, or you could use cis or trans. I'll let you decide what to choose. Okay, so try this one here, the trace nomenclature problem there. Okay. Hey Suparna, did you have lecture today for 1C helix?
Yes, I didn't go though. I fell asleep and my alarm like was not
Oh my
working.
god. It was early morning? Like, what time was it?
Yeah, my class is at 8 a.m.
Oh, that's early. Yeah, that's an early class. Oh my gosh. Okay. Last night we went over trans esterification and Fischer esterification, which went over that general mechanism, addition elimination mechanism or substitution mechanism. Now I want to go over the carboxylic acid derivatives with you before going over the reactions, right? So I'm gonna give it to you in this order specifically, and I'll show you why after. Okay, so there's 1, 2, 3, 4, 5, 6 functional groups here. The parent functional group, like the main functional group of this, is the carboxylic acid. Everything else is considered a carboxylic acid derivative. They derive from the carboxylic acid, right? This one here is an acyl halide. This one here is an anhydride. This one here is an ester. This one here is an amide. This one here is a nitrile. The reason why I put it in this order is because if you go in this direction from right to left, that is increasing in reactivity. Meaning that the acyl halide here, right, where X is like chlorine or bromine, is the most reactive derivative, right? It's the least stable one. It's very reactive. Whereas the nitrile here is the least reactive, right? And that is because of two factors. One factor is about the carbonyl carbon electrophilicity. Oh, wait, that's carbocation. Carbonyl carbon electrophilicity, like there, like that. Right. Let's look at the case of the acyl halide. If we look at this carbonyl carbon right here, this halogen here does have 3 pairs of electrons, right? But it does not really want to donate its electrons to the carbonyl like that. It doesn't really want to do resonance because the halogen here is very electronegative. It wants to keep its electrons. It doesn't want to donate its electrons and do resonance. Another reason why is because chlorine or bromine is a very big atom, so its p orbital does not overlap very well with the p orbitals of the carbonyl carbon and carbonyl oxygen. So resonance is not able to happen very well. Meaning that the positive charge of the carbonyl carbon remains big, right? Because it's not gaining electrons. But if we look at the
If we
amide,
look at the amide,
this nitrogen here
this
is
nitrogen here is
the least electronegative atom
atom.
compared to oxygen and halogen. And because it's the least electronegative atom, it's the most willing to donate electrons to the carbonyl, making the carbonyl carbon of the amide the smallest. Right? Because this carbonyl carbon is gaining the most electrons from this nitrogen. The nitrogen is the most willing to give up its electrons and donate electrons. Right? So that's why the acyl chloride is the most reactive, the amide is the least reactive, and then the ones with the oxygen is in between. Right? Now, I'm going to explain this one here really quick. With the oxygen is in between. Let me make this one a little bit bigger. Okay. The anhydride, right? Carbonyl carbon right here is a bigger positive charge than the carboxylic acid and ester because this oxygen here can do resonance with two carbonyls, the carbonyl to the left and the carbonyl to the right. Because it can do that, its resonance power is split in half, right? So this carbonyl carbon is gaining 1/2 of the electrons of this oxygen right here. Whereas this oxygen here of the carboxylic acid focuses all of its resonance power to one carbonyl. So this carbonyl carbon here is gaining more electrons, becoming a smaller positive charge. That's why it's less reactive than the anhydride, right? Same as the ester. Okay. Now, that is one of the reasons why the reactivity is like that. The other reason why is leaving group ability. So I'm going to circle the leaving groups of these carboxylic acid derivatives in red, which are these groups right here. If we were to kick them out and give them a negative charge, this is what the leaving group would look like. The best leaving group here is the halogen, right? Because this halogen here can handle the negative charge the best, since the halogen is the most electronegative atom. This leaving group here, carboxylate, is the next best leaving group because the negative charge is stabilized by resonance with the carbonyl. The negative charges on these oxygen atoms here cannot do resonance, right? But the negative charge on the oxygen is more stable than the negative charge on the nitrogen because oxygen is more than the nitrogen. So that's why these are better leaving groups than the nitrogen. Okay, so these two factors explain why the reactivity increases from left to right in this order. Okay. Okay, so we're gonna talk about the carboxylic acid reactions first, and then after that we'll go on to the acyl halide reactions, and then the anhydride reactions, and then ester reactions, and then amide reactions, and then nitride reactions. But I want to start off with the carboxylic acid one because that's the parent functional group, right? So let's look at the carboxylic acid reactions. Right, we can convert an acid to an acyl halide using one of two reagents. Let's say we have this carboxylic acid here, and I give you these two reagents. The mechanism is going to be a note card thing. I can go over it if you want, but it's included in that note card that I sent you. But the thing here is that if you recognize SOCO2, that SOCO2 would convert the carboxylic acid to the acyl chloride. If you see PBr3, that PBr3 is going to convert the carboxylic acid to the acyl bromide. This SOCO2 is basically substituting that OH with the chlorine. This PBr3 is substituting this OH with the bromine. And that creates the acyl halide right there. Right? Now, we can create an acid from an anhydride from this right here. So let's say we have something like this. we could go two ways here. We could apply heat, which is that triangle symbol, delta symbol, and that is going to get rid of water, right? And that water is going to come off in the form of that, H2O. And we're going to merge that together to make a ring, which is this ring right here. Right? Where if I highlight the oxygen here in yellow, that's that oxygen there in yellow, like that. Right? And I could number it to keep track of the groups. This is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. We're basically making a new bond between 1 and 5. That bond was not there before, but we made that bond right there. And water left, right, which is that red circle right there. Okay, and this right here is an anhydride, right? It's a cyclic anhydride because we have a carbonyl attached to a carboxylate right there. Another way you could do it is if you do SOCO2, that's going to give you the same thing, right? It's going to give you the same product, but the intermediate here with SOCO2 is this. SOCO2, like we said earlier, is going to convert one of the carboxylic acids into the acyl chloride, right? And when this happens right here, with heat, this carboxylic acid here is going to like attack this carbon, push the bonds to the oxygen. The negative charge on oxygen will go back down, kick out the chlorine to give us this final anhydride right here, right? The mechanism is not tested. Just recognize that if you see two carboxylic acids, a dioic acid like this, with heat or SOCO2, you're going to form a cyclic anhydride, right? We're going to get into the mechanism of this when we get to the acyl chloride reaction, but the cyclic anhydride formation here, you don't need to know the mechanism for it. You just need to recognize that this can happen right here. Okay. Now, the next thing is going to be converting an acid to an ester. And we went over this specific reaction last night. An acid to an ester, the specific name of that reaction is Fischer esterification. Right? And this has to be in acidic conditions. It cannot happen in basic conditions. And we said the reason why it cannot happen in basic conditions is because in basic conditions, that's going to deprotonate the acid to create the carboxylate. And we don't want that, right? We want to create the ester, so we have to be in acidic conditions. So for example, if we have this carboxylic acid here, and we put this alcohol in, and we put acid there, here is the quick way to predict the product without doing the whole mechanism. You're going to substitute this alcohol with this OR of the alcohol right there. So copy and paste everything else of the alcohol and plug in the OR group of that alcohol, which I'm going to color in green right there, which is that OR group right there. Right? That's how you could quickly predict the product if you're going from an acid to ester in acidic conditions. Fischer esterification. The mechanism for this is the exact same as we did last night. Addition elimination mechanism, right? Protein at the carbonyl oxygen and peptide, right? Addition, proton transfer, and then elimination, and then deprotonation. Okay, now we're gonna go from an acid to an amide. But let me see if Helix went over this, because this amide one here is a little bit tricky because the amine is a strong base which will deprotonate the acid. So let me see if he went over this. He probably put heat. Yeah. Okay, yeah. He did, yes. He put that as well. Okay, so here's a conceptual thing, which he could test in multiple choice or explanation, right? This acid to amide thing is tricky. So let's say we have a carboxylic acid right here, and we're given an amine with no base or acid conditions, right? It's neutral. This amine right here, whenever you see an amine, think of this as a strong base, stronger than alcohol, right? The reason why this is a strong base is because nitrogen is less electronegative than oxygen. So that means it's willing to donate electrons and attack, right? So in neutral conditions, this base here is gonna deprotonate the carboxylic acid to generate a carboxylate and ammonium ion, right? So what we did here was an acid-base reaction. And like we said, acid-base reactions are one of the fastest reactions we can have. The base here is the amine. The carboxylic acid here is the acid, right? And he did draw equilibrium arrows where the reaction will favor mostly to this side right here, right? Like these ones will be more in equilibrium than, like more favored than these reagents here. Okay. Now, if you have heat, right, that delta symbol, and time, but on the test, you're just gonna see this heat symbol, that delta symbol. You're gonna form the amide. So let's put that amine there with the heat. You're gonna substitute the alcohol with the NH of the amine, right? Take away one hydrogen, which is that right there. So we converted a carboxylic acid to an amide using amine with heat. And the mechanism is addition and elimination. It has components of both acidic and basic conditions. So let me ask you this, because there's two acceptable mechanisms that Helix accepts for this mechanism here. What do you think the first step is going to be for this mechanism? If we want to convert this carboxylic acid to this amide right here, what is this amine going to do?
Is it gonna protonate the H?
Oh, deprotonate the H? Yes, that is what
sorry, yeah.
is going to do first, right? Because this amine is a strong base. This carboxylic acid is strong acid. But with heat, we're gonna do something else, right? Because that is gonna happen first. But assuming excess of this, if we deprotonate the carboxylic acid, that would not lead to the amide. That would lead to the carboxylate and ammonium, and then we get stuck there. We can't do anything else, right? So you're right, conceptually, like that does happen first, because acid-base reactions are the fastest reactions to happen first. But because we're adding heat here, something else can happen now to form this amide, right? This nitrogen here will attack something else besides the H of the carboxylic acid.
I have no idea.
What atom do you see here?
Wait, so an acid-base reaction doesn't happen here?
Conceptually it does, right? But for Helix exam, when you see heat, something else will happen. It's the addition elimination mechanism we talked about last night, where this is my nucleophile and my electrophile is this carbonyl carbon right there. So the amine is going to attack the carbonyl carbon, push the bond onto the oxygen, and get this tetrahedral intermediate right here, where nitrogen has 4 bonds and a positive charge now, and the OH is right there, like that. Now, from this point, he accepts 2 routes for the mechanism to be correct. One route is, I'm going to show you the shorter route. You could just reform the carbonyl, kick out that OH, even though we say this is a bad leaving group, Helix accepts that leaving group leaving because we have heat, right? If you have heat, then that bad leaving group is able to leave. And
This is so counterintuitive.
counterintuitive. I know. Like usually, like you know how we say this is a bad leaving group here. We don't see that leaving usually, right? The reason why we don't do this intramolecular acid-base reaction where we like deprotonate this group and protonate this group at the same time, because you know how we're used to doing that, right? For the proton transfer steps. The reason why we don't do that is because this oxygen here is a weaker base than the nitrogen. So let's say we did do that. That's gonna lead to this intermediate where oxygen has a positive charge and this nitrogen is now neutral. This is not as favored as the one we have right now. Like this form here is more favored because the amine here is more basic than the oxygen. So this amine here is just gonna like grab the hydrogen back to get back to its original form. And the reason why the nitrogen is more basic is because it's less electronegative than oxygen, right? And because it's less electronegative, it's more willing to attack and donate a pair of electrons, right? So that's why we don't do that, because the oxygen here is not basic enough to grab the hydrogen off of the nitrogen. The nitrogen is like, it's mine, like the hydrogen is mine because it's more basic. You can think of it like that, right? But once we get to here, now it gets counterintuitive, because like what Helix does to get to the next thing is that, actually it kind of makes sense now, because the OH minus is gonna deprotonate this nitrogen to get to this final product amide right here, right? And that's gonna create water. And the reason why this nitrogen here is not gonna grab the hydrogen back to go back to its original form, but it can, but it's not as likely to, is because this pair of electrons here is stabilized by resonance with the carbonyl. And because it can do resonance, it's more stable, more happy, less reactive, right? So that's why this OH minus is now able to grab the hydrogen off of the nitrogen, because it forms a stable conjugate base that's able to do resonance and it's less reactive now. So it's able to occur like this. Any questions on that mechanism from acid to amide?
No, I think I'm just trying to wrap my head around it.
Okay. Let's see. Wait, you could practice like talking me through it, so then it helps you wrap your head around this here. Like explain like why.
Yeah, I think I got it.
Okay.
I think if I look at it long enough, I get it.
Okay. Yeah, this is one of the mechanisms he accepts. I'm gonna show you the other one right now. And both times it took 15 to 20 minutes to fix the projector and everything cover this. Oh, today, like he took him 15 to 20 minutes to fix the projector, and you guys have 50 minutes of lecture, right? So that was like 20 minutes lost, like 15 to 20 minute lost. Oh my gosh. Is he gonna send like another recording like he did last quarter, like for the last time for the lecture? Yeah. What did he end up lecturing off at today? Derivatives, I see. Okay. So the other mechanism is that we have this amine attack the carbon, push the double bond onto the oxygen, get the same tetrahedral intermediate. Right. I'm going in a slightly different order than what Helix teaches, right? Because I want to go over the big main reactions first, and then we'll go over the extra small reactions after the big reactions. Now, once we have this, what we're gonna do is that we're gonna bring in a second equivalent of the amine to deprotonate that positive charged nitrogen. Right? And we get this conjugate acid. Yeah, conjugate acid here, which is going to be the proton source to protonate this alcohol, which we want to convert that into a good leaving group. And this is probably the one that makes more sense. Right? Now, once we have that good leaving group in place, we could reform the carbonyl, kick out the good leaving group, and get our final answer. Like that. Okay, so this mechanism is longer, but it might make more sense because like we're not kicking off this bad leaving group OH. So he accepts both mechanisms. This long one, which might make more sense, and the shorter one, which kicks off this bad leaving group OH. Right. But the reason why it's able to happen is because there's enough energy to do so, heat, and the reason why we're not able to do an intramolecular acid-base reaction, internal acid-base reaction, is because this nitrogen here is more basic. It wants to keep its electrons. It wants to, it's more willing to donate its electrons, give up its electrons, grabbing this hydrogen, right? Okay, yeah. Derivatives. C. Okay, I'm gonna give you a big practice problem. I'm gonna give you guys a big practice problem for 1A and C, and I'm gonna check Kelly's nomenclature work, and then I'll come back and check you guys' work for this one here. Okay. Okay, try these 3 reactions, predict the product. You could draw the mechanism for practice, but there is a shortcut to predict the product to save time on the exam. Try these 3 right here. Okay. Yeah. See ya. Okay. Kelly, did you have the nomenclature problem I gave here as practice? Yeah, let me see what you got so far. I have my phone this time. Wait, why did you text me? Oh, I see it. What the heck? You just sent now. Okay. Let's see. So you put okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. And 8 dimethyl, you got that substituent correct. It is a 2 nano because the main chain is 9 carbons long, where carbon 2 has the alcohol, so that is good. At carbon 5, there's this substituent right here, which is 1, 2, 3, right? Which the propenol part is correct. But for this one right here, you have to put parentheses. So it's going to be 5, parentheses, something propenol, 2, non, nan, no. The reason why is because the alkene could be here where it is now, or it could be here, right? And this could have been a single bond. To specify, we're gonna put 1 propenol to show that the alkene is coming off at carbon 1 of this propenol, right? This one here is too vague. This one here, we don't know if the alkene is right here or if it's right here, based off this name. But because the alkene is coming off of carbon 1, we put 1 propenol, and we have to put parentheses for that. Does that make sense? Why we have to put that right here? Yeah, okay. So that's good. Let's check your stereochemistry. At carbon 2, this is 1, this is 2, this is 3. Going this way is S, and it stays S, because the lowest priority group is on the back side, so we maintain its configuration. 2R. How did you prioritize the power center for carbon 2? Like, what did you try? What was your thought process for that one? Oh, but you got the same priority, right? Like you got the alcohol as 1, this whole group as 2, and this whole group as 3. That's good. Okay, so if it's like that, going this way is counterclockwise, which is S. So the 2 here should be an S. And at 5, because I did not give you wedge or dash, we don't know if 5 is R or S, right? Because there's no wedge or dash on 5. 5 is the current center. But we don't know if it's R or S. You got tricked. You got tricked. Okay, so I'm going to erase that right there. I wonder how... The stereochemistry I wanted you to think about here, the other one, is this alkene. Like, would that be E or Z? Or cis or trans, if you could do that. This alkene right here. I don't know if, like, the alkene here is the substituent. We could put cis, because this is cis right here. If you make a line through the double bond, the 2 substituents are on the same side. You could put it right there, right? Let me see her lecture notes to see if she prioritized in practice with that. Because the alkenes that she did... Oh yeah, she did put stereochemistry. So yeah, we still can put stereochemistry here. This is E, so we could put E. And because we only have 1 alkene, we could be generic with it. We could be like... Or actually, to be more specific, let's just put it right here. E. That's also correct. I like being more specific. So the full name is going to be 2S Yep. I was thinking the ABCs in my head to see what comes first, M or P. Yeah, that M goes first. So 8, 8. dimethyl 5 E1. No, this is not E. This is Z. The same side. Cis. Right, the two groups are on the same side. Z. Z1 propenol 2 no nan no. So that is the name of this structure. Right, the Z here represents this alkene is Z. Right, but the alkene here is the substituent, not the main chain. In this last example here, we could not put E or Z because this alkene here cannot be E or Z at all, even if it's the main chain. Right, because like if you look at this carbon here, there's no higher priority group. But in this case, there is a higher priority group for this carbon, right, which is this whole group. And there is a higher priority group for this carbon, which is this group right here. And we see that those two highest priority groups are on the same side of the line, making it Z. Okay. Any questions on this nomenclature problem? Yeah, it was sneaky for sure. The 5 here had no stereochemistry, so you can't assign RS there. And then the alkene one was the new one this quarter. Yeah. Yeah, so don't forget your R and S's from when it's in A for nomenclature. Do you remember R and S, Suparna? From when it's in A?
Oh my god, yeah, of course. That's my favorite.
Oh my gosh, that's your favorite? Like counterclockwise, clockwise? Oh my gosh.
Chirality in the bag.
Wait, who did you have for one in A? One in B you had Levens? What how about for one in A? Was it Ling?
Like a graduate TA.
Ling, right?
Yeah, I
Yeah,
was
Ling,
not
Ling,
a
Ling.
fan. No offense.
I don't know. Like yeah, he was there for that one summer session only, and then he never came back.
I was doing physics too over the summer, so with 118A, and that was not it.
Oh my god. Like, oh my god, summer session 1. Did you know about me in summer session 1? Or did you know about me in summer session
I
2?
think I heard about you in summer session 2.
Uh-huh.
Yeah.
Wow, I see. Uh-huh.
Otherwise, I think I would have also gotten a really good grade in 118A, but I didn't. I also kind of slacked off. But he went at the speed of light with his lectures, and he wouldn't take any questions, and they were like 2 hours long, and I wanted to kill myself.
Oh my god. And you were in lecture too? Like, and you wanted to ask questions like during lecture, but he wouldn't like
No, he
take your
said there's no
questions?
time, and then he literally would write his notes at like the speed of light and had like
Mm.
chicken scratch handwriting, and I could not keep up. I didn't even understand anything because you're so busy copying down notes.
Oh yeah. Oh
And
my
then the
god.
TAs were like not it for that class. Like the TAs were just like so chill. They were like, yeah, it's nothing. Like the quizzes were really easy in discussion section, and then the
Mm-hmm.
exams were like crazy hard. But because people were retaking it, like I think more than half our class was retakers. The average was so high, and I was like, damn guys, like can't even pray on your guys' downfall because this is the second time you guys are seeing the material.
I know. Oh my gosh. But luckily you made it through. So that's good. But then you made it to
Barely.
Leuven.
The curve made it. The
Mm.
curve, like,
Yeah. But then you got
it
a
was
range
so
of like
bad.
OChem professors, Ling, Levens, and now Helix. That's pretty good.
I don't think he said he was a TA associate. Like he said he didn't get his PhD to become, he was becoming a professor, but I don't know.
Oh my god. Dang.
That was really fun.
Wait, what's your major? What's your guys' major at UC Davis?
I'm MPB.
NPV? Let's see.
Yes.
That's good. Let's see. How about you, Kelly? Okay, I'll stop recording soon. Okay, Suparna, were you able to do these 3 reactions?
Yeah, I basically just replaced the alcohol with all of them.
Nice. Cl. And this, we're gonna replace this with OR, which is this. Right, the H is gone to make that oxygen neutral. And were you able to do the last one? It was kind of sneaky. It was kind of a weird nucleophile here. Were you able to get this as your answer?
Yeah.
Okay, that's good. That's good. Okay, so that is very nice and easy to predict the product. Just substitute the alcohol with whatever the nucleophile is. The mechanism, because you have the no card, you could have that no card too. So that's the good thing about midterm 1. You know, these are the big reactions here, like the common big reactions. For carboxylic acid, right? I'll give you another thing here before we end today. You know how we went over the list of reactivity, like ranking list right here? We finished the carboxylic acid reactions. We're going to see that for addition and elimination reactions, the more reactive derivative can create any of the less reactive derivatives in one single step easily. Right? Let's ignore the nitrile. The nitrile is not like a derivative. It is a derivative, but it's a cousin, right? It's a cousin because there's no carbonyl. There's no carbon of one oxygen. So this acyl chloride here can create any of these less reactive derivatives in one step.
Dang.
Anhydride here can create any of these in one step. It cannot create the acyl chloride in one step because the acyl chloride is more reactive than the anhydride, right? The carboxylic acid here can actually create like these in one step because it's the parent functional group. But note that the reaction to go from here to the acyl chloride is not an addition and elimination reaction, right? Because if we use SOCO2 or PBr3, that is some other mechanism, like SN2 like mechanism. That is not addition and elimination.
You're saying like one reagent can go from like one to all the lesser reactive ones?
Yeah, like the more reactive derivative, which is this acyl chloride here, can go to any of the less reactive derivatives in one single step.
Oh, dang. Okay.
Yeah, using only one reagent. Only one reagent.
Oh, wow.
Yes, only one reagent.
Wait,
now if you
that's so helpful for synthesis.
it is because like like if once you know the reactivity list here, then there's a lot of like tricks and tips here. Like when we go over synthesis, I want to show you a lot of strategies, but we gotta know all the reactions first, right? And
Okay.
I did make a chart here that summarizes the reactions after I go over all of them in detail, which is like this right here, like the interconversion between the carboxylic acid derivatives. You see here, the acyl chloride is the most reactive derivative, right? These are the different reagents you can see. We see that it can do the most amount of reactions. The thing you see in red are the products. If you see a product, that means that it can do a reaction, right? Anhydride can do the same amount of reactions because anhydride is like pretty reactive as well. So think of acyl chloride and anhydride as the top two most reactive derivatives, acyl chloride and anhydride. Everything else is less reactive, and they would require like acid or base catalyst. If you look at the carboxylic acid, it could only do 3 of these reactions. Ester, you could do 5 of those. And then the least reactive ones, amide and nitrile, it could only do 2 of those right there. But we'll go over these in detail. And then when we go over the organometallics with the Grignard reagent or organolithium, and this one here, I remember telling you that this is 118B. We don't have to think about it, but it does come back for 118C. This is the organogroup right here. Which was used for like 1,4 addition, but this is going to be used in a different way for this unit for carboxylic acid derivatives.
Oh my god, I forgot 1,4 and 1,2 addition.
1,4, 1,2 addition. That part here would not be on the unit, but this reagent will be back.
Okay.
Yeah. Okay. Hydride reducing agents like lithium aluminum hydride, NaBH4, we went over that. These are the new ones, Dibol and this one here, the new one for 118C.
Got it.
Mm-hmm. And those were the big reactions I wanted to go over, and here are the other reactions to know for the midterm 1. These are quicker reactions like oxidation of primary alcohols, Grignard hydrolysis, and stuff like that. Okay. Yes. So if you look at this ester here, this ester can create the amide in one step, but it cannot create the anhydride in one step. It cannot create the acyl chloride in one step because it's less reactive than them, right? And here's another thing. There's a type of reaction called hydrolysis. Hydrolysis converts any derivative back into the carboxylic acid, the parent functional group. It's like a reset. like a factory reset. Any of these derivatives here can go back to this parent functional group through hydrolysis. Right, and we'll go over that tomorrow. It's a lot right now. It's kind of overwhelming right now. That's why you get the whole 3 weeks to learn about these reactions. There's a lot of like reactions here. Yeah. Okay.
Okay.
That's good. That's good.